As we finished, or nearly finished, the previous lecture, we had talked about surface tension, which is this compressed layer of molecules in a liquid at the surface, and indicated the strength of it being quite large to support insects, etc. And I just thought this morning I would go ahead and demonstrate this surface tension by a couple of simple demonstrations. First of all, here I have a Petri dish, and if you can notice, it's about a half of inch of water in it. And very carefully I have placed a needle, a sewing needle, which of course is made out of iron, which is much more dense than water. I have carefully placed the needle on top of the water. It is actually floating on the surface tension. You can see it move there as I blow on it. It's not suspended. It's not on the bottom moving. It's actually floating on the surface tension itself. If I break that surface tension by using a surfactant, then because the density now will become greater than the density of the bulk solution, then of course the needle should sink. Let's leave that there just a second, and let's look at a slightly larger system first, and then we'll come back to that one. Here I have a beaker of water, and I have a little strawberry basket. The density of the plastic itself is just a little bit more dense than water. However, it will displace enough volume that it will not totally sink, but it will actually set on top of the water as long as I do not break the surface tension. So if I haven't had too much coffee so that my nerves are still halfway smooth, I'll try to go ahead and place this on top of the water. And we see that it is on the surface tension, and it's supported there. And again, now if I break that surface tension, then we should see the container sink. So we'll go ahead and place a couple of drops of surfactant, or commonly known as soap. And I'll move this back away from the edge a little bit here again. Get it more in the center of the beaker. We'll put a couple of drops of surfactant in there, and we should see once we break the surface tension, that's a lot of surface area there, so I may need, well, I shouldn't need that much. Oh, there it goes. All right, we finally broke the surface tension with the soap, and once the surface tension was broken, we no longer have that dense layer at the surface, and of course the basket then sank. It doesn't sink, as I say, all the way to the bottom because the density of the plastic is not too much more dense than the water, and finally, of course, it displaces enough volume that it tends to float just at the surface. We still have the needle over there floating, however, and we'll go ahead. Maybe my surfactant is, well, it feels okay. And we'll go over here to the needle that is floating on top of the surface. Again, you can see that it moves freely on that surface. And we'll add a drop of surfactant to this container. And immediately the needle has dropped to the bottom. One way you can tell it's now on the bottom, you can see the change in focus. When it was at the surface, we saw a lot of width because we were seeing actually the curve of the water reflecting the light as well as the needle. Now that it's at the surface, notice it doesn't move. Now that it's down on the bottom, of course, it no longer has that distortion. So that surface tension really is very, very strong. When you think of the density of a steel needle floating on top of that surface, it obviously shows that that strength, that surface tension strength, is quite large. All right. If you have a steady hand, you can do that. You can float the needle on top of the water. One thing that if you want to try it yourself to demonstrate it to a brother or sister or something, the way that I would suggest doing it is cradle the needle in a small piece of Kleenex. Just take a single sheet of the Kleenex, lay the needle on, carefully set it in, then let one end of the Kleenex drop. It will soak up water and you'll be able to slide that Kleenex right back out from underneath the needle and leave it floating. Pretty difficult to hold your fingers and actually set it in without your fingers breaking the surface tension of the water. So it's easier to do it with a little bit of Kleenex. The last part of the lecture, previously we talked about, or began talking about solids, and mentioned that we're going to be looking at 4 different types of solids, which are molecular, ionic, metallic, and covalent. And in the molecular solids, the ones that we have looked at already, we said that the forces were similar to those in liquids. In other words, the intermolecular forces are the same as when we're dealing with a liquid. So again, we have hydrogen bonding, we have dipole-dipole forces, and we have the dispersion forces. And in this particular case, we looked at 4 examples of molecular solids. That means that in the solid there are individual molecules and held together then by these attractive forces. And we looked at iodine, dry ice or solid carbon dioxide, water in a solid state, ice, and sugar, normal table sugar that we're looking at here. One of the properties of some of the nonpolar solids especially is that they can undergo sublimation. And sublimation was this direct phase change from the solid to the gaseous state without a liquid in between. Even water undergoes some degree of sublimation. For instance, if I were to take say a wet towel on a very cold winter day, temperature well below freezing. If I were to take that towel and hang it outside, first of all I would notice it would freeze, of course, the water. But if I left it out there for several hours and I brought it back in, I would notice that it was almost dry. It was almost dry, meaning that even though the water initially froze, some of the water molecules continued to escape, undergo sublimation from the solid. We never had the liquid state. It goes directly again from the solid to the gas. So even water sublimes to some extent. Or in the wintertime we may notice that even though the temperature is well below freezing, and even though we don't have salt or anything to lower the freezing point of the ice, that the ice will disappear even on very cold weather. Again, it's undergoing sublimation. If we have very low humidity, a little bit of wind or something like that, water will undergo a reasonable rate of sublimation. So the water will disappear. Or if you have ice cubes in a frost-free refrigerator, you'll notice that the ice cubes slowly decrease in size. They're not melting, they're merely undergoing sublimation. They will actually slowly change from the solid to the gas, and the ice cube will actually become smaller. Frost-free keeps the freezer part, then very low humidity, and you do have some airflow through it, and this increases sublimation. All right, let's look at the second category of solids, which are the ionic solids. Now, ionic solids are held together by electrostatic force, by charge differences. In other words, pluses attracting minuses. And there are 2 factors that we have to consider when we look at the forces involved in ionic solids. That is, the size of the ion and also the charge on the ion. These are the 2 controlling factors. If it's electrostatic, if it says ionic, quite obviously we're talking about charged particles or ions. So these are the 2 factors that affect how strongly they attract each other. Now, one key characteristic of ionic solids as compared to molecular solids If we melt a molecular solid and put electrodes in, remember earlier in the year when we were looking at solutions, we talked about electrolytic solutions, solutions that have ions in them and can conduct a current. Well, we can do the same thing with liquids. We can put electrodes in and see if they conduct. Well, molecular solids, if we melt them, put electrodes in, we would get no electrical conductivity. But if we melt an ionic solid and put electrodes in, we get a very good conduction of electricity. In other words, the ions are able to move in that molten state. So that's one way of testing to determine if the solid we have is ionic or molecular in its nature. Melt it, see if it conducts. If it conducts as a liquid, it would indicate that in fact it's an ionic solid. All right. And not conduct as a solid. That would be one of the other characteristics. An example question here is predict the bonding forces. In other words, predict the increase in melting point. The stronger the ionic forces, the higher the temperature will be before you can pull them apart, before you can melt then the solid. In other words, the stronger they attract each other, the more difficult it is to put them in the molten state. All right? So if we look at these four compounds, and we're now going to try to put them in increasing order of boiling point, meaning that the last one would be the one that has the strongest attractive force, and the first one would be the one that has the weakest attractive force. First of all, let's look at the charges here. Rubidium is a +1. Element number 37, it's in the first column of the chart, indicates it's a +1. Chlorine is a -1. Chlorine's in the 7th column over there as a nonmetal ion, will always be -1. Magnesium, +2. Second column of the periodic table. Chlorine again, -1. Magnesium +2, we just said that. Oxygen as a nonmetal over there in the 6th column of the periodic table. As a nonmetal, it's going to be a -2. We've already talked about magnesium, so again it's a +2. And then fluorine, we notice, is in the same column as chlorine, and so therefore it's a -1. Now, we said that size and charge. Let's focus on charge for a minute. Which of those four compounds would have the least charge involved in it? The first one I heard somebody say, okay? The first one, RBCl, because it just has a +1 and a -1. Notice that all of these have at least a +2 in it. That's more charge. That means that they're going to attract more strongly to each other. So the weakest forces in this one, the lowest melting point then, would be rubidium chloride. That's the first one. If we had a mixture of these and began heating them up, the first one to melt would be the rubidium chloride. All right. Which one should have the greatest attraction, electrostatic attraction? MgO, I heard somebody say, correct. Because there we have a +2 and a -2. So we have the maximum of the negative and the maximum of the positive of these compounds we're looking at. And so up here we have MgO, the highest melting point compound. Now the other two that are left both contain a +2 ion and a -1 ion. So they are identical then in their structure as far as charge. Then, if that's the case, what we would have to look at would be the size. Well, in each case, the magnesium is the same, so obviously the magnesium doesn't change in size. So the question is, which, the chlorine or the fluorine, is going to have the smallest or largest size? Either way we want to look at it. Now, in terms of electrostatic attraction, the smaller the size, the greater the attraction. The smaller the size, the greater the attraction. Well, you see, if I have two things, and one has the size of this, and the other has the size of this, and they both have a -1 charge associated to them, quite obviously this -1 is spread out over a whole lot greater volume than this one. And so therefore the charge density is greater on the smaller ion. Is much greater on the smaller. So therefore the attractive force is inversely related to size. The smaller the size, the greater the attractive force, if that's the only thing making a difference. So we're looking at chlorine and fluorine, two atoms in the 7th column. So and both are going to be -1. Now, just thinking of our atomic structure, chlorine has one more entire principal quantum number of electrons. Would you expect it to be bigger or smaller than fluorine? Greater. And so therefore we would draw F and Cl. Again, each one has one minus charge in there, but chlorine is a larger atom. Matter of fact, we talked about, I think, general trends of atomic size. We said as we went across the row, size gets smaller. As we go down a column, size gets larger. Okay? So chlorine is going to be larger than fluorine, bromine larger than chlorine, and so on. And so therefore, this, with greater size, would have a weaker attractive force than would fluorine to the corresponding magnesiums. So we would have then MgCl2, and then finally MgF2, and the highest melting point of the whole works, MgO. All right? Any questions on that? Let's just throw in one more here quickly, and let's ask, how would this one fit into our picture up here? Where would we predict that it would go? Well, we see that as far as the charge, it's the same as the magnesium chloride, but the difference would be, what's the difference between the calcium and the magnesium in this case? And again, using our periodic chart, we would see that calcium is one notch, one row below the magnesium, meaning that the calcium would be a larger, if this were calcium, it would be larger than the magnesium. I didn't draw that much larger, but we'll make it a little bit bigger there. The calcium is larger than the magnesium. If the calcium is larger, therefore its attractive force is less, meaning that its melting point would be lower. And so therefore we would predict that calcium chloride should fit into our melting sequence just before the magnesium chloride. Again, we have a +2 -1, so the charges are the same. It's merely then the size difference that we're looking at. Okay? Well, this gives you just a quick overview of a few compounds, and ionic compounds now, and their corresponding melting points, and a little bit about some of their uses. The first one we see there, sodium iodide. Okay, and notice that if we looked at the relative aspect here, sodium iodide, that's a +1 and a -1. And potassium chloride is a +1 -1. And calcium chloride is a +2 -1. Sodium chloride +1 -1. And calcium oxide +2 -2. So quite obviously we'd expect the calcium oxide, which has the only 2-2 electrostatic force, to have the highest melting point. And in fact, that's exactly what we see. So calcium oxide, or lime as it's called, has a melting point of 2,614 Celsius degrees. Table salt, sodium chloride, has a melting point of 801 Celsius degrees, and sodium iodide, which is added, if you buy salt, it will usually say, or most people will use iodized salt. Iodized salt contains not only the sodium chloride, but it contains some sodium iodide to provide our body with the necessary iodine that we have to have for proper thyroid function. All right, so it's an iodine substitute or supplement in food. Now, those two would make sense because we're looking at iodine and chlorine, and if we look on the periodic chart, we see that iodine is 2 rows below the chloride, means the iodine is much bigger than the chloride, therefore its attractive force would be less. And so we see that in fact it is on the first or the lowest melting point of the whole works. So by looking at size and charge for ionic compounds, we can make some general predictions as to at least melting point trends. We couldn't necessarily say that looking at a compound like iron 2 oxide, we couldn't predict what exactly the melting point would be, but at least within a series of compounds we can predict how they would behave. All right? Now the next type of solid that we want to talk about are the metallic solids. And if we think back to what we've talked about on a periodic chart, remember that everything to the left of this jagged line is a metal as an element. Those are all metals. Hydrogen, let's exclude it because it has sort of unique behavior because of its single electron structure. But everything else is a metal, and out of all of those metals, there's only one that's not a solid at room temperature, and that is mercury. So when we talk about metallic solids, we're talking about basically all of the elements to the left of my pointer at this point, other than for mercury. And if we cool mercury off, it will become a solid also. But metallic solids. Now, one of the characteristics of metallic solids is that they conduct an electric current, whether they're in a molten state or solid state. They conduct as a solid. Ionic compounds will conduct as a melt, as a molten substance. Molecular compounds won't conduct any time. So molecular will not conduct, ionic will conduct in the molten state but not conduct in the solid state, and metallic solids will conduct in both the solid and the molten state. Well, how do we account for this behavior of electrical conductivity? Well, we talk about a sea of electrons. Let's just look at 2 atoms here. Let's say let's pick 2 sodium atoms. All right, and so we have a sodium atom and we have a sodium atom here. And they have a positive nucleus. Each one has a +11 nucleus. And surrounding that are 11 electrons. But when we start stacking these atoms, one on top of the other, etc., that those electrons now actually become intermingled. It's very difficult to tell whether this electron belongs to this nucleus or this one. And actually, if we looked at it for sodium, we would have it's in the 3rd row, so we would have a 3s with 1 electron in it, and a 3p, these are the valence orbitals, with nothing in it. Well, these electrons, then from one atom to the other, are quite mobile by moving through these valence orbitals of other atoms. And in fact then, if we take a strip of metal like this, and we have the positives in here, surrounded by this sea of electrons, if we put one electron in this side, an electron will be displaced out that side. Actually, electrical conductivity is almost an instantaneous phenomena. If I hook up a wire to a battery, as soon as I touch the battery, the electrons are flowing over here. In other words, all the electrons, this whole cloud or sea of electrons, all of them shift instantaneously because we've applied a charge on that end. As a matter of fact, that's very important, because if that didn't occur, if we were to, say, start up a power plant like here in Springfield, and we have a power plant out in the southwest part of town, if we were to start up that power plant today and have to put electrons into a conductor and have that electron we're producing today appear in the light bulb here, it would probably take us 5 to 10 years before we would ever get the light turned on, for the electron to move through all of that distance to here. But that's not the way it works. The instant that power plant starts and that generator turns and applies a negative charge to this side of the wire running from here out to the plant, this light bulb immediately lights as soon as they start producing power. And of course, if that weren't the case, then metallic conductors would be very useless as far as their electric ability. All right, so we have this sea of electrons in metals, and that's what accounts for their electrical conductiviity. Now, one other property that metals have is that we say that they're ductile and they're malleable. Ductile or ductility is the ability to be drawn into wire or stretched into shape. So metals are ductile. This is the way we produce metal. We take blocks of metal and put them into a die and push or pull them through in very thin strands of wire, and of course that's what the ductility means. Malleable means that we can hammer it or pound it into different shapes and forms or into thin sheets. Because these nuclei, and that accounts for both ductility and malleability, if we go back up to this structure here, because there is no definitive bond between any particular atoms, these atoms are easily displaced, and it doesn't bother them any because they still have this same number of electrons. And so when we hammer something, we can shove them around, we can stretch them, we can move them into different positions with very little energy or effect. Okay? So metal solids have the property of being ductile and malleable. Now, as far as melting points of the metals, they vary considerably. Mercury, even though it has a fairly large mass of 200, is a liquid at room temperature. And yet lithium, which has a mass of only 7, is a solid at room temperature. Gallium, element number 31, which has a weight of 70, putting a piece of gallium into your palm of your hand, the body temperature would be sufficient to melt the gallium metal. It melts at about 36 Celsius degrees. So we see a tremendous range. Oh, and then if we look at tungsten, the metal, the wire that is used in the light bulb, the metal that we can flow electrons through and heat to white hot so that we get white light produced, doesn't melt until well over 2,000 Celsius degrees. And yet it's not nearly as heavy as mercury is. So quite a contrast in the melting points of metals. We can just look at a few of the melting points here to see some of the differences. Here we have magnesium, a metal in the 1A family, or excuse me, in the 2A family. Over here, melts at 650. Iron, 1535. But yet tin here again, which is a much heavier element, element number 50, 119 roughly, melts at 232. Platinum melts at almost 1800 Celsius degrees. Mercury melts at minus 39 Celsius degrees. It's a liquid at room temperature. As a matter of fact, it's a liquid down to rather low temperatures. We go over here, silver and gold melt at fairly close, only 100 degrees difference in the melting point of those two. We see silver and gold right here. But here's silver and gold melting at temperatures of about 1100 degrees. And right next to it is mercury, which melts at minus 39. So you see it's very difficult to identify any particular trends when it comes to the properties or melting properties of metals. All right. The fourth type of solid are what we call covalent solids. And covalent solids now imply that they are held together, that the particles in the solid are actually held together by sharing electrons, by truly covalent bonds. Okay? And the covalent solids have some of the strongest bonding forces of all the solids that we have. Carbon exists as a covalent solid. As a matter of fact, we have actually we now have four. We have four different allotropic forms of pure carbon. Pure carbon can be found in what we call carbon black or soot. If you burn a candle, put a plate above the candle, you get this little black deposit. That black deposit is basically pure carbon. It's unburnt carbon from the wax in the candle that hasn't been totally converted to carbon dioxide. So some of that carbon comes off then as elemental carbon, carbon black. Carbon black is industrially important. Matter of fact, we commercially produce carbon black. Carbon black is used to add to rubber, synthetic rubber products, to increase its wearability. The reason that a car tire is black is not because rubber is black. Rubber is the synthetic rubber is sort of a vanilla looking or a tan looking color. A tire is black because we add considerable carbon black to the rubber mixture to increase its wearability. Natural rubber is pretty soft, or even synthetic rubber is pretty soft. And so therefore it would tend to not wear very well. And so to increase the wearability, we add then carbon black. Carbon black is actually just little groups of carbon atoms. So each one of these would represent a considerable number of individual carbon atoms, but just little bundles of these, little bunches of that is carbon black. Graphite. Graphite is pure carbon. Graphite is used as a lubricant in weapons, in firearms, where we don't want an oily, gummy, petroleum-type lubricant, or in a sewing machine or something like that, graphite. And the reason graphite is a good lubricant is graphite occurs in sheets, so it's just long carbons like this, like that, in sheets just like pieces of paper. And so this would be a sheet of graphite, and this would be a sheet of graphite, and there's really nothing in between the two other than for mass attraction, and these slide pretty easy over each other. So these little sheets of graphite are fairly mobile, very little friction, and provide then an excellent lubricant. But also, graphite has the ability to conduct an electric current. There are empty valence orbitals in the carbon, and electrons can move through, and so graphite behaves as a metal. It's a good electrical conductor, even though it's a nonmetal. And is used quite extensively in making wires for like spark plugs spark plug wires on an automobile. Instead of using a hard metal like copper, it's just a plastic tube stuffed with graphite. And the advantage is that the tube then, working back and forth as the engine moves, doesn't break. Whereas if you have a copper wire, that constant moving back and forth, if you take a piece of wire and just go back and forth, or a hanger, and do this a few times, pretty soon it breaks. You can break the copper wire in the spark plug, and therefore then you start getting some gapping, some sparking that's occurring, and loss of energy. Graphite can be used as a electrical conductor. Diamond is pure carbon. The difference between diamond and graphite is that in diamond, each carbon now takes up its normal tetrahedral geometry, like such. And so this carbon now would have, of course, attached to it carbons. So it would be another carbon and carbon down and carbon down up and so on. Whoops, wrong direction there. Carbon. So it's a tetrahedrally bonded covalent group of carbon atoms that make up diamond. Diamond is the hardest material, which would imply that it has the strongest bonding, the strongest interparticle bonding forces of any of the types of solid. Diamond is our standard for hardness. One of the uses of diamonds is, of course, because it is so hard, it can be used as a cutting material or a polishing material. Now, in nature, some of the diamond that occurs in nature that was produced under very high pressure and high temperature is actually, the diamond is produced from graphite. Graphite is a grayish black color. Diamond, of course, jewelry diamonds are a clear glass-like color. In the conversion from graphite to diamond, then if we don't get all of the graphite converted, we end up with a diamond that has a gray or black color. And these diamonds are used for industry, for cutting and polishing purposes, for producing drill bits that are used to drill for oil. We need something hard to grind through all the rock to get down to the oil, 5,000, 10,000 feet deep. And we use diamond bits to do that. But it's not diamonds of the type that we would use for jewelry. The diamonds we use for jewelry, then all of the graphite essentially has been converted, and so we have a clear material rather than a gray or a black material. One of the last form of carbon is groups of 60 carbons hooked together in a unit that looks like a soccer ball. If you've ever looked at a soccer ball is actually composed of a cloth that is pentagon shaped, and then the next one is hexagon shaped. So they're pentagon hexagons, 5-side, 6-side pieces of leather that are then sewed together. And when you do this, when you hook 60 of these alternating, 30 of each together, it bends around and comes back into a perfect sphere. And so you have a round soccer ball because of using that type of structure of cover coating. There's a carbon, a pure form of carbon, carbon-60 as it's called, or sometimes called buckyball. The ball comes from the soccer ball, and the bucky comes from Buckmeister Fullerene, who was actually it was Buckmeister was the person who studied the geodesic dome structure, an architect, which has this sort of general, again, structure of 5 and 6s to make a dome, in other words, half a sphere instead of a total sphere. And so Buckmeister, then the Fullerene, which is actually the name of unsaturated hydrocarbons or carbon, and it nicknamed buckyball. Buckyball had a lot of publicity in the last year because the Nobel Prize in Chemistry was awarded to 2 chemists from the United States, from Rice University, and one from the University of Kingston, I think it was, in England. The 3 of these people were the researchers that identified this new form of carbon only 10 years ago. And so buckyball is a fairly new discovery, and it's somewhat odd for people to really receive Nobel Prizes that quickly after discoveries. And so these three chemists, two American, received the Nobel Prize in Chemistry for their discovery and identification of this C60 molecule, pure carbon molecule called buckyball. A lot of research is going into it. There are things of looking at that this ball, we might be able to put medicine inside of it and use the carbon structure to transport then medicines to particular areas in the body, or putting in metal ions into the structure and using it for various medicinal purposes. So a lot of research is now being done on the buckyball. The last one is silicon dioxide, and it has three allotropic forms. Quartz, which is a three-dimensional structure, and quartz looks a lot like diamond. It's SiO2 units then in a tetrahedral geometry, covalently bonded. Quartz is, again, a very hard substance, not as hard as diamond, but fairly hard. Quartz looks a little bit like diamond, and sometimes it's even called or used as synthetic diamonds in jewelry. For instance, there's a lot of quartz in Arkansas, and there's some places that we talk about or hear advertised Arkansas diamonds. Arkansas diamonds are pure quartz, not pure carbon. All right? Mica, which is like graphite, is a two-dimensional structure. So I'll just put graphite here because it's similar to that. It's made up of sheets, pieces just like paper. And if you got a piece of mica, you could actually sit there and pull one sheet of mica off of the other as you went along. And finally, this one has been in the news for the past 10 years and still keeps showing up, and that's asbestos. Asbestos comes in a fiber, a long continuous chain of these SiO2s, so it's a fiber type material. And of course, asbestos was determined to be a contributor or a possible contributor to lung cancer. Asbestos was used for many years as an insulating material around pipes for heat conduction and cooling, in walls for insulating from heat and cold. So a lot of asbestos was used. Then, when it was determined that asbestos might be a contributor to lung cancer, the federal regulations were that any building that had asbestos in it had to have it totally removed. And so a tremendous amount of tax dollars was spent in removing all of the asbestos. This building was insulated with asbestos on all the heating pipes in the building. And about 8 years ago, they came in with special crews, totally protected in full suits, breathing masks, had to tape everything off, lock the doors, seal the building off, close down the air conditioning or air circulating system, and went into the areas and took out the asbestos. And they did this in many public buildings, schools, etc., throughout the nation. Well, one of the more recent studies shows that there is only one type of asbestos that essentially causes lung cancer. And 99.9% of the asbestos used for insulation was not that type. And so we now have spent a lot of money probably removing something that we probably really didn't have to. But again, only because of further research was that found. All right? So the covalent solids. Now, what happens when we heat a solid? We talked about what happened when we heated a liquid, and we noticed that we have a graph that looks quite the same. As we begin applying heat, we heat the solid up. But once the solid begins its phase change, which we call melting, or the reverse of melting is fusion, once we begin that, then the temperature doesn't change until all of the solid has melted. Once all the solid has melted, we can begin to heat the liquid. So now over here we're heating the liquid. But notice that the temperatures remained a constant as we went through the phase change. Now, the other day we talked about the molar heat of evaporation, which was how much energy it took to change 1 mole of liquid to a gas at its boiling point. The molar heat of fusion, as it's referred to, is the amount of energy needed to change 1 mole of solid to liquid at its melting point, or the amount of energy that would be given off as 1 mole of liquid went back to being a solid. So either melting, fusion is actually the freezing, the solidification process. Melting would be then, of course, the process where we're changing from the solid to the liquid. Now, again, we do have some values, some numeric values for and oh, there we go. The molar heat of, oops, well, it disappeared on me someplace. Oh, maybe this is, let's see if this is it. Nope. Well, I don't see my chart right handy here. So I guess I can't get an actual numeric value. Well, if all else fails, we'll turn to the resource that we have, which is our text. And so just quickly on page, I heard somebody say, 347 in the text, or looking for table, which has the melting points. Oh, that's where it was. I do have it. The melting points of the material and also the molar heat of fusion. I do have it. Okay. Here are some of the molar heat effusions for the different materials. Water, iodine, sodium chloride, calcium oxide. Now, again, we would expect that things that have high melting points would probably have high molar heats of fusion. If it's difficult to melt them, it must take a lot of energy to do so. And so we see that the things that had very high melting points, like calcium oxide, well, we look at it, it has a very high molar heat of fusion, 51 kilojoules per mole. Tungsten, high melting point, 35 kilojoules per mole. Water is actually fairly low, 6.01. Now that's low, but when we think of its mass of only 18, that is proportionately very high as far as a molar heat of fusion. So with those pieces of information, it is possible to do a quantitative calculation of the amount of energy needed to change then from one to another. And let's just quickly ask the question, how many kilojoules of energy are needed to melt 1 pound of table salt? 453.6 grams of sodium chloride. So, kilojoules would be equal to 453.6 grams multiplied by, looking for the molar heat of fusion of sodium chloride, that was 30.21 kilojoules per mole of NaCl. And of course, that won't work for units, so we would have to convert from moles to grams. So multiplied by 50, let's see, we'd have 23 and 35, so 58.35 grams of sodium chloride per 1. Whoops, I better do it the other way around. We better do it 1 mole over. So again, paying attention to the units does help us set the problem up right. 1 mole of NaCl per 58.35 grams. Notice grams would cancel, moles would cancel, and we would be left with kilojoules. All right, in our next lecture, we'll spend a little bit more time talking about heating and cooling of materials and calculating quantitative values for that process.